All right, so it is Monday, May 31st, Memorial Day, and it is 8 o'clock. And so we're going to go ahead and get started with some EIGRP that we want to talk about this week. And this will be the first of many EIGRP sessions. And one of the things that the text does not, or I should say the packet tracer activities do not reinforce is the EIGRP information. And so the first thing that I wanted to talk about is the Eigrp Rfc. And so if you were to go to, or you could just simply Google RFC 7868, and that's going to bring you to this document right here. And this is the EIGRP request for comment. You can see it's informational, so it's not an internet standard. And what's interesting is the individuals who are the authors of this document, Donnie Savage, has been a maintainer of EIGRP since right around 1995. So he is really sort of considered the father of EIGRP. And this document goes into a lot of good detail. And we're going to be referring to a few of the sections in this document tonight with respect to the K values when we talk about the coefficients or the composite metric where EIGRP is making its best path decision. And how does EIGRP do that? And so we'll be talking about that this evening. We'll also talk about one of the shortcomings in the RFC, and that is the fact that it doesn't include the stub network functionality. And so this document details a lot about EIGRP, but it doesn't go into detail about the stub network. In fact, if I was to search in here and say stub, you can see that there are zero matches for the stub network. So we'll scoot back up here to the top of the document, and we'll come back to this document in a second. So let's dive in. And let's start to do some EIGRP configuration, and let's talk about what that looks like and what we need to do and what would need to be done. Now, the majority of this environment is already configured, because once I show you how to do the EIGRP configuration, you would then do something similar on all of the routers that are in this environment. And so I apologize, the font size is a little small. And unfortunately, there's nothing I can do to make the font size larger over here. So we're on router 13, and let's take a look. If I say show IP interface brief, and I'll be sure to detail the commands that we're running, you can see that we've got 3 interfaces configured. We've got 2 physical interfaces configured, Gigabit Ethernet 00 and Gigabit Ethernet 01. And then we have a loopback address configured. Now, remember, a loopback address is nothing more than a virtual address. And it's basically just an interface that is virtual that runs in software. And so if I was to try to ping 10.1.13.1, and the way that the segments run between the routers is it's going to be 10 dot the lower router number dot the higher router number, and then dot the router number. So 10.1.13.1, that's the IP address right here on that interface for router 1. We're on router 13. So I'm just pinging to show that I've got connectivity. And then let's see if we can ping router 3. So that would be 10.3.13.3. So connectivity to router 1 checks out. Let's check connectivity out. Oops, sorry. We'll check connectivity out here to router 3, and you can see we've got connectivity to router 3. Now, as I said, the majority of this environment over here is already configured for EIGRP, because we don't want to spend an hour going to router trying to do EIGRP config when we can do it a couple times and we'll know exactly what it is that would be required. So here I am on router 1. And if I was to say show, oops, sorry, let's pull that back. We'll get into privilege exec. If I say show run and pipe it to section router EIGRP, you can see that we're using EIGRP classic mode. Now, classic mode is 32-bit mode, right? And so when we're talking about setting up routers with EIGRP, you can do it either in classic mode, which again is 32-bit mode, meaning the metrics scale out to 32-bit values. And the drawback with this is that you have an IPv4 configuration stanza and an IPv6 configuration stanza. And we're going to see what name mode looks like tonight. And we're going to see, I'm going to show you how you can convert seamlessly with no hit at all from a classic mode EIGRP configuration to the named mode EIGRP configuration. And so here you see we've got router EIGRP1. We've got a whole bunch of network statements here on router 1, because as you can see, router 1 has, what is it, 1, 2, 3, 4 physical connections to other routers that are running EIGRP, and it has a loopback interface. So on router 1, if I was to say show IP route EIGRP, what we would end up seeing is all of the EIGRP routing information that has been learned by router 1. And you'll notice it sees the loopback address, and we're advertising those loopback addresses on each router. And the loopback address on every router is simply the router number 4 times, right? So router 1 is 1.1.1.1 is the loopback address that we advertise. Router 9 would be 9.9.9.9. And so you can see we have all of the routing information here, but we don't have anything for router 13, right? Because we haven't configured router 13 yet. Now, you'll notice in some instances, and the loopback address for router 9 is a good example of that. And we'll let this finish running here. And again, this is a little slow. It's a virtual machine. You can see down here, it's actually chewing up quite a bit of the CPU that's being used. But if I scroll back up here, you can see that if we look at what we learned about the route to get to router, the loopback address of router 9, which is the 9999 here, you can see that the administrative distance is 90 because it's internal EIGRP as opposed to external EIGRP. And then we have these via statements here, right? And so these would be considered the successors. In other words, these are the next hops. And you'll notice that the cost, right, the metric, the composite metric is the same for all 3 of these. So we've got 3 equal cost paths in order to get to this router 9 router, which is 9999. Now, we can even drill down further by taking a look. And so this is the routing table. We could take a look at the neighbor table. I could say show IP EIGRP neighbor, and that's going to show me the EIGRP neighbors that exist. And again, this H, which I've never really understood why Donnie Savage and the EIGRP team used H. It stands for handle. But really what it is, it's the order in which these neighbors were learned, right? Or the neighbor adjacency was established. And so 0 would be the first one, then 1, then 2. And so it shows us additional information about the neighbor relationship. Now the Q count, the QCNT right here, should always be 0. If it's not 0, that means that there's something wrong. It should always be 0. Nothing should be queued up. And then you can see the hold time in seconds. You can see the uptime. How long has the adjacency been up? 1 hour and 18 minutes, right? So that's just a way to gather some information. You could also say show IP EIGRP neighbors detail. Now, this is a command that is a great command that you will not find in Packet Tracer. And so I always like to show this command because it shows you the same information initially, but then you get some additional information that gets added in, right? And it'll show you topology IDs from the peer. It'll show you the version of the EIGRP software. It'll show you if there's retransmissions, retries, prefixes that have been learned. So it gives you some additional information. So show IP EIGRP detail is very helpful. And it's very helpful when you're setting up stub networks with EIGRP, right? Because it'll show you how this router views other routers if those other routers have the stub flag set for whatever reason. So let's do this. Let's go ahead and let's go to router 13 and let's walk through an EIGRP configuration here. So we're going to get into global config, and it's simply autonomous system number 1. So I'm going to say router EIGRP. If I do a question mark, you can see that we have a choice of autonomous system numbers from 1 to 65535. Now, right below that, it says EIGRP virtual instance name. Now, this would be if I was doing named mode or 64-bit mode. So think of it like this, sort of the original legacy way to do EIGRP is what I'm going to show you right here. Then I'm going to show you how we can convert the configuration from the legacy config to the named mode, which is sort of the new way to do it because it's based on what's referred to as address families. So let's go ahead and do router EIGRP 1, and we'll set the EIGRP router ID to 0.0.0.13. And again, the router ID is used primarily when you're doing redistribution. So if I'm redistributing between EIGRP autonomous system numbers, this would prevent loops from forming. In other words, if my router ID on router 13 is 0.0.0.13, and I get a routing update, and my router ID is in the update, that means that there's a loop there, that advertisement came all the way back around to me. And so that's the primary purpose for the EIGRP router ID. Now, the EIGRP router ID is very different in terms of functionality when we compare it to the Ospf router ID, because Ospf is a link state routing protocol, period. It is not a hybrid routing protocol. It is not advanced link state. It is a link state routing protocol. And the discussion question from this week was kind of driving to get us to that point and understanding that it's the algorithm that dictates the classification of a routing protocol. So the link state routing protocols that are out there that we're interested in are Ospf, and then there's intermediate system to intermediate system, or IS to IS. Now, both Ospf and IS to IS are link state routing protocols where a database will be built for each of the areas that exist in your Ospf routing domain, and every router in any area will know details about all the other routers in that area. And again, I'm stressing in the area in which the router sits or is a member, right? So area 0, the backbone area. If it's not an area border router or an autonomous system boundary router, right? If it's just a backbone router, then it will have a single link state database, and it will have all of the information about all of the other routers in the area, in area 0. So the router ID with Ospf, think of it like a social security number or a fingerprint. It's a unique identifier that's used to identify that router in the area. With EIGRP, there isn't a database that's built that has all the information about all the other routers that are in the autonomous system. Now, can we get some information on specific routes? We can, and I'm going to show you that here in just a second. However, there is no full map of the entire autonomous system in EIGRP. And if you look at the design that we have here, and the routers with the green dots, those are the only routers that are on. And I've got, like, this router here is off, router 12, router 7, and router 6. Those routers are off. So just a quick note there. So what happens in EIGRP is router 9 is going to advertise its loopback address, that 9999 address. It advertises it to router 11. Well, router 11 then advertises it to router 10. Now, router 10 knows, and I'll show you how router 10 knows. Router 10 and all the routers that get this advertisement know where it originated. They know the router ID of where the route originated, but that is all they know. And the only way they know how to get to that route is by what their neighbor has told them. And so router 10 would advertise to router 8. And then router 8 advertises to router 5. And then 5 is going to advertise to 4. And that's where we're going to hop onto here. So let's jump onto router 4, right? Whoops, let me open the console up here. So we're on router 4. And let's take a look at the routing table. So I'm going to go ahead and say show IP route EIGRP. And what that means is show me the routing table, but only show me routes that I've learned via the EIGRP routing process. And as we page down, we can stop right there. And let me go ahead and do, and it's a little behind here because there's, as you can see, there's quite a bit of routing information involved. And here we go. So we're interested in this guy right here. Now you can see router 4 knows, and this is all router 4 knows. It only knows that to get to the 9999, I go out gigabit Ethernet 01. That's the interface, which is right here, on which it learned about that route. And that is the only path that that router can take to get to the 9999. So it knows the interface out which to go. So how does it know that it originated from router 9? Well, for that, if we say show IP EIGRP Topo, which is short for topology, and this is another table. So we've seen the neighbor table for EIGRP. We've seen, we've seen the routing table for EIGRP with the show IP route or show IP route EIGRP. Show IP EIGRP topology shows me the other table that exists with EIGRP, and that is the topology table. However, you can be very specific with this command. And you can see right here, I can give it the exact network that I've learned about that I'm interested in finding more information about. So I'll say show IP EIGRP topology 9999/32, because that's the route that we've learned. We'll hit enter and take a look at the information that we learn here, right? And the show IP EIGRP topology command is going to come in very handy when we start to talk about feasible successor, the reported distance, the feasible distance, the computed distance. So these are all a bunch of terms that really kind of make EIGRP challenging for learners. And here is where you can see the originating router. So EIGRP knows the router ID of the router that originated this advertisement. However, that is all EIGRP knows about router 9, or I should say router 4. That's all it knows about router 9, is that that is where this route originated. Again, it came to 11, then to 10, then to 8, then to 5. And so this is what we refer to, and I commented on one of the discussion posts, this is what we refer to as routing by rumor. And that is a distance vector behavior. And what routing by rumor is it simply means that router 4 has no idea other than to get to that network, I'm just going to send my traffic to router 5, because router 5 is telling me that if you need to get to the 9999, come to me. And that's what we refer to as routing by rumor, because there is no map that gets built into a database where all of the links are described for the individual nodes that we know about based on their router IDs, right? That doesn't happen in EIGRP. Now, again, when you use the show IP EIGRP topology command, you can see the originating router. And the same thing would be true if I said show IP EIGRP topology. If we change this to, let's say, let's bring that back, 11.11.11.11/32. We should see that the originating router for that network is router 11, and we do, based on the router ID right there. All right, so let's take a step back here to router 13. And we've set our router ID. We kind of talked about what the router ID is for and compared and contrasted it a little bit with the Ospf router ID. So now what I could do is I could say passive interface default, right? But then I'm going to have to say no passive interface gig 00, and then no passive interface, is it gigabit Ethernet 01. Now remember, I'm sorry, yeah. So remember, there's two ways we can approach this. We can say passive interface default, and then all interfaces are made passive by default. And so if we wanted to no passive the interface, in other words, it's an interface over which we're going to be establishing an EIGRP adjacency, which in this case, gig 00 and 01 that go to routers 1 and 3 respectively, right? We would want those to be not passive, because what the no passive interface does, or I should say what passive interface does, is it suppresses the sending of EIGRP hello packets, right? And you can't form an adjacency if you're not sending those hello packets, which are being multicasted out to 224.00.10, right? And other routers are listening for that multicast advertisement. And if the router isn't multicasting the EIGRP hellos, then an adjacency is not going to form. So now that we've got that sorted out, what we can do is we can now add in the network commands. Now, Packet Tracer is going to want to see network statements like this in the activities that you do. So I'd say 10.1.13.0.0.0.255. And this would be considered your classic network statement, where I've got the network ID identified and I've got the wildcard mask for that network ID, which is the inverse of whatever the subnet mask on that interface is. Now, I know that all the interfaces on the transit segment here, everything's a /24. And so a 24, which is the CIDR notation, would be in dotted decimal notation 255, 255, 255, 0. So the inverse of that is 0, 0, 0, 255. That's the wildcard mask. So on current versions of iOS, you can do this, and I'll hit enter. So there's our first network statement, and we should see in short order here that we have an adjacency come up with router 1, and there it is. Now, I'm going to put another network statement in, and this is going to be a network statement for the loopback address, which is a /32, meaning its net mask in dotted decimal notation is all 255s. So 255, 255, 255, 255. Well, the inverse of that is 0, 0, 0, 0. So let's go ahead and say network 13.13.13.13.13, 0, 0, 0, 0. Where are we at? There we go. All right. Now, so there's two additional ways. So I showed you how you can do it with the wildcard mask and the network ID. I showed you how you can do it if it's what we call a host route. A /32 is referred to as a host route because it's an IP address for an individual host IP, right? It's not representing a network of IPs. So now we've got a network statement still to go here between router 13 and router 3. Now there's two additional ways that we can bring these networks to be running the EIGRP routing process. And let me show you the first one here. And what you can do is you can say network 10.3.13.0. And I'm going to show you this way first. So there's the network ID for the transit segment between router 13 and router 3. And you can actually put in the subnet mask in dotted decimal notation. And this is totally acceptable because iOS is smart enough to know that when I hit enter, that I entered in the subnet mask in dotted decimal notation. And so what it's going to do, and you can see that proves it worked because the adjacency just came up between router 13 and 3. So now when I say do show run section router EIGRP, what do we see? And we'll give it a second here. And what you're going to see is that it converted the dotted decimal subnet mask into a wildcard mask. So again, in Packet Tracer, you can't do this. However, in the real world, you can. And again, understand that Cisco on their exams, not only in the course, but in the CCNA or CCNP, they love to give you funky net mask lengths like a 27 or a 28 or a 29. And then you've got to come up with network statements and you need to know how to do the wildcard mask, right? And so they do that. However, in reality, you can type in the net mask and EIGRP converts it to the wildcard mask for you, right? So you don't have to sit there and try to figure out, well, what's the inverse if it's a /28 or 29? And so that makes it a little bit easier. Another way to do the exact same thing, so let me remove that statement. And let's go back to the network statement here. We'll say Control A, and that is not what we wanted to have happen there. There we go. And so we'll say no network. So we remove the network statement because there's another way to enter it. And this is the Cisco best practice. And if you're going to be moving on, or you think you're going to be moving on to the CCIE exam, this is universal for OSPF and EIGRP. This is how you would look to do your network statements in both OSPF and EIGRP. And that is, you're going to indicate 10.3.13.13, the exact IP address of the interface, right? And a quad 0 subnet mask, like I showed you for the loopback address, right? You can do the same thing for the physical interface over which you want that EIGRP neighbor adjacency to be formed, right? So I hit enter and we're going to get our adjacency. It's going to come back here pretty quickly and everything's going to be good to go. And we're going to have the adjacency back, and there it is, between router 13 and router 3. And this is typically what you see when you're talking about Cisco best practice, right? Now, there's nothing wrong with the wildcard, with using the wildcard mask, right? However, this is very, very specific, right? Because maybe you've got the 10.3.13 carved up into like multiple /29s or something like that, right? So by being able to put the exact IP address of the interface, right, there's no question as to which network statement would be applicable to which interface. And again, a long time ago, there's some point there was a question I had seen where they showed you a couple network statements and then wanted to know which interface the network statement, one of the network statements applied to, and they had carved it, this one subnet into a bunch of /29s, right? And so it's good to know about that, but this is how you're typically going to enable the EIGRP routing process on an interface across which you're going to establish an adjacency. And you might be asking, well, wait a second, if you do that, does that mean that the advertisement of that interface right there that connects here to router 3, that, like, let's say I come over here to router 9, am I going to see a /32 with just that single IP, or is EIGRP smart enough to know that, yeah, my network statement is a /32, It's the exact IP address on the interface. And is EIGRP smart enough to maybe look at that interface and see what is the subnet mask on that interface, and then advertise that as the EIGRP network that is going to be advertised from router 13. And so easy enough for us to see. We'll come on to router. So we'll go all the way over here around the loop to router 9. And let's say show IP route EIGRP. And this is going to be listed out with our 10.3.13 subnet. And let's scoot by the loopback addresses there. And you can see those loopback addresses are shown to be /32s. And where are we at? There it is right there. I apologize for the small font here. So 10.3.13.0/24, right? It's a /24. So EIGRP is smart enough to know that if you put the network statement in with quad zeros, it's going to look at the configuration on that interface to see what is the subnet mask. And then it's going to advertise it for you with that subnet mask, right? Like you would want it to do. And so that's a good thing. All right. Now, another note about EIGRP, and I can't remember if it's in the ENCORv book or the ENRC book, which is the Enterprise Advanced Routing and Services book, which is going to be CMIT-456, which will run in the fall. One of the books, and actually it may be in both, they use that word hybrid. So to be clear, EIGRP is not a hybrid routing protocol, just like OSPF is not a hybrid routing protocol. And Donnie Savage, who again is the father of EIGRP, has stated multiple times that it is not a hybrid routing protocol. The problem was that when EIGRP kind of was first started to gain some traction, was that some of the Cisco marketing material and then some Cisco press books started to refer to it as a hybrid. It's not a hybrid routing protocol. So remember that. It's an advanced distance vector routing protocol. And so why is it advanced? Well, it's advanced because it uses more than just the hop count. If this was a RIP environment, and you've been reading about RIP and distance vector routing protocols, all RIP cares about is how many hops away is it to get to the destination. And whichever route or path or vector has the lowest hop count, that's the path I'm going to travel. And so that doesn't make much sense, right? Because if there's 3 hops, but those are 100 gig connections, and there's 2 hops that are 64 kilobits a second, it's going to choose the 264 kilobits a second. Now, are there ways where you could engineer that it takes those that takes the 300 gig connections? Absolutely, right? Because you can do layer 3 traffic engineering, but by default, RIP is not very intelligent. And so EIGRP, and technically it was IGRP, which is the predecessor to EIGRP, which is the Interior Gateway Routing Protocol. Again, Cisco proprietary, and I'll talk about the RFC again here in a second. However, it had a lot of issues. It was classful, right? So it didn't support classless interdomain routing. That's CIDR notation we use. All the networks were classful, and that's a problem. It did not bounded updates. What am I trying to say? Timed updates. So like every 90 seconds or 60 seconds, I can't remember which it was for IGRP, it would literally flood its whole routing table out, whether there had been a change or not. It just kept sending its whole routing table out with the EIGRP information. And so that was problematic. And then the biggest problem was that IGRP was susceptible to loops forming when the network was trying to converge. And so Cisco quickly realized that they had better enhance IGRP, and that's where we get EIGRP, the Enhanced Interior Gateway Routing Protocol. And EIGRP doesn't have any of those problems I just mentioned, which again and I know it's like semantics, but it's advanced distance vector, because EIGRP and the diffusing update algorithm dual ensure loop freedom, right? So the topology is free of loops at all times. And it accomplishes this by using what's referred to as successors and feasible successors, most importantly, that have to meet a feasibility condition. And I'm going to touch on that here in a second. So we've got router 13 up and running. It's got EIGRP going. And we've seen that if I come back over here to router 9, and if I was to say show IP EIGRP topo for the 13.13/32, we should see that that route is being advertised. And there it is. And again, the originating router. So we know where it originated from, but the only way we know how to get there is based off what router 11 is telling us, which is routing by rumor, right? I don't have a database that tells me all this information about router 13 and all of its links. So now what are we going to do here? Let me make sure I've covered everything I wanted to cover. Yep. Okay, so now we're going to focus on the conversion. So let's say that you're in an environment that has the classic 32-bit mode configuration, which is what we're running right now. So let's say show run section router EIGRP. And here's my classic configuration. We've got our router ID statement. We've got our network statements. If I was trying to set some other parameters in there, we could. So here's how we convert this seamlessly to the named mode configuration. We say router EIGRP1, and then I say EIGRP and it's update CLI, but let's take a look at some of these other commands that we could add in here, right? So there's an event log. I could create the event log or manipulate the event log size. We could log neighbor changes and warnings, right? So these are things that you would want to think about implementing if you're going to implement EIGRP. But there's the upgrade CLI. Now, after I say upgrade CLI, I have to put a word in, or more specifically, a name. So, because this is why it's referred to as named mode, because we can give it a name. But the major difference is not the fact that we give it a name, although that is a big difference. We're not giving it an autonomous system number initially. We're giving it a name, but that enables us to have 64-bit metrics, right? And that's a huge improvement in terms of granularity. And what I mean by granularity, and I'm not going to run this command just yet because we're going to talk about a couple things here before we do that. What I mean by granularity is with the classic mode, EIGRP can only differentiate links from 1 kilobit a second up to 10 gigabits a second. Anything faster than 10 gigabits a second, EIGRP treats it as if it was 10 gigabits a second. So if you had a 100 gig link and a 10 gig link, classic EIGRP doesn't have the specificity or the granularity to deal with differentiating which of those two paths is better. And so that was a major drawback. Now, Ospf has the exact same problem. It's dealt with in a different way with the auto cost reference bandwidth setting. With EIGRP, there is no auto cost reference bandwidth setting, right? So with classic mode, a 10 gig link and a 40 gig link or a 100 gig link or a terabit link, they're all looked at as equal in terms of preference. And so that is one of the things that named mode gives you. It gives you the ability to differentiate between links. I think it goes all the way up to 655 terabits per second, which is insane, right? And we are far from that being common in enterprise networks, right? In terms of, two links between routers. So again, but it obviously room for growth there. So that was one of the drawbacks with classic EIGRP. Now, let's take a look, and we'll do it from router 4's perspective here, because it'll be a little bit easier to talk about with router 4. So remember, router 9 has got this loopback address. So let's say show IP route, not show IP route, sorry, show IP EIGRP topo for the 9999/32. And I'm going to get an error message there. I left out one of my 9s. All right, so let's drop that last 9 in, and there we go. Now, this gives us all the information we need in order to determine what the metric or the cost is going to be. And here's where we're going to talk about the composite metric values for EIGRP, because these are some of the most confusing sort of features or aspects of EIGRP that tend to sort of make it a little more difficult to understand what's going on. So you can see here that we've got our, oops, sorry, that is our successor right there, is 10455. So from router 4's perspective, the successor is just the next hop router. Who do I go to get to this network? And you can see here that it is the 10455, and that's the IP address on the router 5 interface right here. Now, when we take a look here, you can see the composite metric is 131840, and then it shows this other 131584, because one of those is the feasible distance. The other is what's referred to as the reported distance. And so I'm going to say feasible distance right now, but I'm going to show you that it's really not the feasible distance. If you were to say show IP route, and I'll hit enter here, and we'll take a look at that 9999, and what we're going to see is you have the administrative distance for internal EIGRP here for the 9999, and hopefully it stops scrolling here. And it is right there. And this is one of the drawbacks of simulators. They're pretty intensive in terms of CPU and memory. So here it is. And that value right there, you will see that that value is sometimes referred to as the feasible distance. And I'm here to tell you it is not. That is the computed distance. And I'm going to explain the different terms. So the first number in the brackets on the left-hand side of the /, that is the administrative distance for internal EIGRP routes, which is 90. Over here, you have the cost or the metric. It's the computed distance. It's my cost, router 4. That's my cost to get to the loopback address over here on router 9. Now, router 5 is also advertising to router 4 its distance. And that is what we refer to as the reported distance. And so let's take a look at router 5 here. And because we want to match those two numbers up that we saw with the show IP EIGRP topology command to make sure that we've got the right values. And so here, if I say show IP EIGRP topo for the 9999/32, and actually, I'm sorry, let me just say, whoops, sorry, pull that back. We'll say show IP route for the, and I'll just leave it at that. And we'll scoot down here. And you can see there is the distance right there. That's the metric, 131,584, which is what we're going to see right down here for router 5. And again, this, where are we at here? Let's slide back down. There we go. And so this, that is the metric. That's the distance, right? That's the cost for router 5 to get to the loopback of router 9. And you'll notice that number is pretty familiar, right? 131,584. And so what is the reported distance? Well, the reported distance is the distance that router 5 tells router 4 that it's going to cost router 5 to get there. So when router 4 gets the update from router 5, it then increments that cost with its cost to get there, which the cost is all based on the composite metric values. And so let's talk about that. And this is why I didn't want to switch to the 64-bit mode yet, because then the values change and these numbers get much, much bigger. So let's step back over here to router 4, and we could even scroll up a little bit, and we would end up seeing that we saw, there it is. There's the reported distance, right? So router 5, from the router 4 perspective, router 5 is the successor, because that's the only way that router 4 can get to router 9. And so that is going to be the next hop, and that's what we see here. And there's that next hop value. But the composite metric, right? With Ospf, it's very simple. Ospf uses the interface bandwidth, and that is it. That's how Ospf by default figures out which cost or which route is best. It's based on lowest cost. Lowest is always better, right? So Ospf just looks at the different outgoing band interfaces and looks at the bandwidth on the path to get to the destination, and it uses this equation 10 to the 8 divided by the bandwidth in bits per second, right? With EIGRP, it's a little bit more complicated. So EIGRP uses what are referred to as composite metric values, or K values. So how can I see these K values? Well, you can say show IP protocols, right? And you need to have EIGRP running. And this is going to show me those K metric values. And here they are. We'll let them pop up. And you've got K1 through K5. Now, when you transition to named mode or 64-bit mode, you get this new value called K6, which is not being used. So let's talk about these composite metric values, because this is how router 4 is determining its cost to get to the loopback of router 9, right? Because it needs to figure out which is the best way for me to go. Now, granted, there's only one way to go. We're going to come over here to 13, and we're going to make some changes in here so that we've got some a little more challenging look at the environment from router 13's perspective when making its decision on which is the best path. But for right now, let's just look at router 4. So K1, that represents bandwidth, right? In terms of what is going to be evaluated. Now, these are composite, or sometimes you'll hear them referred to as coefficients, because if it's a 1, right? So K1 equals 1, K2 is 0, K3 equals 1, K4 is 0, K5 is 0. So what's going on here? Well, if there is a 1, in other words, if K1 equals 1, or anything greater than or equal to 1 up to 255, it means that that K value is considered in the calculation for the best path, right? If it's a 0, it means it's not. And so you can see that K2, K4, and K5, and we're talking about bandwidth, reliability, reliability and load, which are on interfaces, and we're going to see that in a second. So the only thing that we're using by default is the bandwidth and the delay. And the delay is really tied to the serialization delay. How long does it take an interface to serialize and then process and forward on a packet? And it's all based on the speed of the interface, right? So slower interfaces take longer, and faster interfaces can do the serialization much quicker. So, but let's be a little bit more specific. K1 is the lowest bandwidth. It's looking for whatever the lowest bandwidth along the path would be. That's the value that's going to get used for the K1 value, lowest bandwidth. So all of these links are the same. And I'm going to do some changes over here, but all of these links are the same right here, right? So they're all a gigabit, meaning that the K1 value is going to be 1 gigabit per second, right? Because that's the slowest link speed along the path. Now, with the delay, it's the cumulative delay. In other words, from router 4's perspective, and this is very important to understand, the delay on the outgoing interface here, the outgoing interface here, it's only the outgoing interfaces that are calculated up. So it's not every interface where it looks at what the delay value is. It only looks at the outgoing, and we're here on router 9, and it's going to treat that loopback address. There will be a delay for the loopback address because it's virtual, loopback 0. And so it's looking at the outgoing interfaces to see what their delay is. Well, how do we see that? Well, let's come over here and say, show interface, and I guess we'll just say gigabit 00. And this is how you see all of the values I've just talked about. The bandwidth, the reliability, the load, the delay, they're all right here. And let's take a look right down here. And there is the bandwidth, right? And this command outputs the bandwidth in kilobits per second. So you can see right there that we've got 1, 2, 3, 1, 2, 3, a million kilobits a second is a gigabit a second. Here's the delay. Now, the delay gets shown, that little U sec, it gets shown in microseconds. And this is one of the most confusing things with EIGRP. The output shows us the value in microseconds, but if I wanted to change the delay, I put in the value in tens of microseconds, right? So, and actually, let me make sure I've got that straight, because that's something I always get backwards here. So interface gigabit Ethernet 00. So if I say delay, let's make sure we're accurate here. Yeah, so it shows it in microseconds, and we put in, if we wanted to change it, we put the value in tens of microseconds. So what's happening here? K1 and K3 by default are the only values that are used by EIGRP when determining the shortest best path, right? Now, you might be wondering, well, doesn't it make sense? Why wouldn't I turn on K2, K4, and K5? Because if I, why can't I, shouldn't I be using all these other values too? And the answer is no. And here is why. When we're talking about reliability and we're talking about load, right? Those are point-in-time snapshots of whatever those values are at the time you turn those K values on. Meaning, if I turned on K2 and K4, and then 30 minutes after I turn them on, the network gets completely flooded with traffic, and those values are shifting, EIGRP does not take that into consideration, right? It looks at it when it's enabled. When you turn the K1, or I'm sorry, the K2 and the K4, or the load reliability, those are point-in-time value snapshots, right? So there is no, I'm sorry, I'm just taking a look at something here real quick that popped up. Yeah, absolutely. You're very, very welcome. And again, we're recording everything, so everybody will be able to view this as well. So the K2, the K4, those are point in time. So like when I enable that, if I wanted to turn that on by setting K2 to 1 and K4 to 1, right? Then those are on. When I activate those, whatever the value is for reliability and the load, that's what it is at that time. Meaning, again, if the network starts getting saturated, EIGRP doesn't go back and look at those. And that's why those are not on. And the other reason, all of those composite, the K values, those came from IGRP, right? So they're kind of like holdovers from IGRP. And that was the same problem there, is that they don't update, right? They're not updating. So why enable them if they're not going to update to accurately reflect what is actually going on in your network? So that's why only K1 and K3 are enabled, bandwidth and delay. And now I'm going to show you a real easy way. Whoops, sorry, clicked out of the window there. Let me show you a real easy way, because you might be thinking to yourself, well, wait a second, are you telling me, oh boy, let me get this back there. There we go. You might be thinking to yourself, well, wait a second, are you telling me that I'm going to have to get onto all these routers? I'm going to have to go into all the interfaces, look to see what the speeds are, look to see what the delay values are, and add all that stuff up to try to figure out, excuse me, what the cost would be? And the answer is no. There's a much smarter way to do that. We've already run the command, whoops, sorry, show IP EIGRP Topo. And for the network in question, and I forgot the last 9 there. I apologize. I keep typoing that out there. So let's get back here. And there we go. So the information, all the information you need, right? Because again, remember, all we need is the bandwidth and the delay. I need the lowest bandwidth speed along the path on all those outgoing interfaces. And I need the cumulative delay to add the delay up for all those interfaces. Well, let's take a look here and see, do we have that information? Well, there it is, minimum bandwidth, 1,000,000 kilobits a second. What about the total delay? There's the total delay. And here's your reliability. Here's your load. And so for reliability, you want it to be 255 out of 255. That means I'm 100%. I'm totally reliable. Load, on the other hand, you want it to be like lowest out over 255, right? Lowest value you can get, which is like 1 over 255, because that means I'm not really overloaded. I'm kind of like way down here, not being used at all. So I'm 1 over 255. If that was like 240, you're probably having a lot of latency and issues in your network. And I'm going to talk about MTU here in a second, because this is another one of these urban legend values that people say, oh yeah, no, EIGRP uses the MTU to calculate the composite metric value. No, it does not. I'm here to tell you it doesn't, right? So, but we'll come back to MTU in a second. So we have right here, we've got the minimum bandwidth and we've got the total delay, the cumulative delay. So there's the command, show IP EIGRP topology, and then just list out the route you're trying to get to, and you've got your values right. EIGRP tells you there it is. So now what we're going to do is we're going to flip the script a little bit here, and no pun intended by script, but I'm going to show you, and this is what I use to sort of display how the value gets calculated, right? So you can see here, we've got 1,000,000 kilobits a second. We've got 50/50, so 5,050 microseconds. So what I'm going to do now is I like to show learners this, because if you're going to be calculating this, right? Sure, it's great to know how to do it manually. However, why would we not just simply write a, oh, I'm sorry. I'm on the wrong tab. I was on a router and I tried to cat a file out and I'm like, that's an odd response. So I've got a Python script here, right? So let's walk through this Python script here for a second. And let's see what it's doing, right? So it's going to prompt the user right here. What is the minimum bandwidth along the path in kilobits per second? Well, the show IP EIGRP topology gave us that command. So I'm going to type that in and you see what it does here. So this is the reference bandwidth for the calculation with classic EIGRP. And how many zeros do you have there? 1, 2, 3, 4, 5, 6, 7, right? And we divide it by whatever that bandwidth value is that we just entered in. And then I'm going to print out that after dividing by 10 to the 7, the bandwidth value is, and it's going to print out what the value for the bandwidth would be. Because you take 1 followed by 7 zeros and divide it by the lowest bandwidth in kilobits per second. And then the delay, right? We simply take the delay, right? We prompt for what the total delay is, and then we divide by 10. And then you add the bandwidth value to the delay value, and you multiply by 256. So it's really not that, I mean, there's really like, you've got two mathematical operations you're going to do here. You've got this third one, and then that's going to give you your composite metric value, and that's it, right? So it's a big, scary equation when you look at it, but when only K1, the bandwidth, and K3, the delay, are being evaluated to give you the composite metric, then all you need are those two values, and you can simply take the 1 and take 10 to the 7, 10 7 zeros, divide that by the bandwidth, kilobits per second, take the delay, divide by 10, take the results from those two operations, add them together, multiply by 256. Now, you might be wondering, why are we multiplying by 256? Now, remember, I keep harping on the fact that classic EIGRP is 32-bit mode, or 32-bit, right, in terms of 32-bit metrics. Well, it just so happened that IGRP was 24 bits. Say 24 bit, 24-bit, right? Well, the difference is 8 bits. So if there's an 8-bit difference, and we're looking at 8-bit positions, 2, 3, 4, 5, 6, 7, 8, and we value all these bit positions out, right? We're going to come up with 256, right? Or 255, I think, when we do it, when you're looking at it in the binary, but they bump it, they multiply by 256, right? And that's why we can, I say 32-bit, and IGRP was 24-bit. So that 8-bit difference, we go ahead and multiply by 256, because remember, again, this equation came from IGRP, right? It came from IGRP. All right, well, let me clear the screen here. And so let's go ahead and let's see if this script works. And let's go ahead and run it. So I'm just going to simply say ./eigrp.py. So enter the minimum bandwidth along the path, 1, 2, 3, 4, 5, 6. And let me double check that to make sure that that's what we had. 1, 2, 3, 4, 5, 6. Yep, so that's what we had. And you can see here, so after dividing by 10 to the 7, the bandwidth value is 10. And then the cumulative delay in microseconds was 50/50. And what is the value we get? 131840. And that should look very, very familiar, because there it is right there. Now, you might hear that referred to as the feasible distance. It is not. It's the computed distance. And so let me talk about that for a second. So the feasible distance, and to see that, I would want to say do show IP EIGRP topo. So just the topology table, not any specific route, because that's where we're going to see some of these different values. And remember, we're on router number 4 here. And so let's scoot down. And you can see in the topology table, it even points out, and let's take a look at the loopback of, oh, I'm sorry, we don't want the loopback of router 4. Let's take the loopback of router 5 down here, right? And you can see that it actually states that this value right here, that is the feasible distance. You'll notice the values happen to be the same, but it doesn't say that's the feasible distance down here in the parentheses. And this right here, right, that's what we're seeing when we do that show IP EIGRP topology command and give the specific route, is we're getting this information right here. But the feasible distance is up here. It just so happens that the computed distance, which is, I'll say CD, is initially the same as the feasible distance, which is the FD, right? But the computed distance can change if something changes in the environment and the route doesn't go active. And so what I mean by that is you can make a little change to the delay, and as long as the route, it doesn't force the route to go active, it doesn't force EIGRP to recalculate things, then you'll see that there will be a difference in those values. And so let's see if I can demonstrate that for you right now. So if we were to look here on router 13, and I was to say, and let's get our prompt up here. All right. And I was to go into show IP interface brief. So let's go to the interface between router 13 and router 1. So how about if I say show IP, and let's do this. Let's say show IP route, and I'm just going to look at the loopback address for router 4. So I'm looking for the 4444, because you can see we've got multiple ways that we can get there, although it's preferring the path through. And so maybe the 9 is going to be a better candidate here. And the 9 is only showing the 1 because I was making some changes. So let's do this. So can't change that. So yeah, we'll just deal with the 4 here, and we'll see if we can make the change. So you can see for the 4444, it shows the administrative distance, and it shows 131,072, right? So the cost for router 13, the composite metric value, the cost for 13 to get to that loopback address on router 4 is 131,072, right? So let's take a look at the delay on the interface, right? Because when you're manipulating EIGRP, you want to use the delay value, not the bandwidth. Because if you manipulate the bandwidth, if you have QoS running, or if maybe you have another routing protocol running, you can affect and impact those services by changing the bandwidth. But delay, Ospf doesn't look at delay. It looks at the bandwidth of the interface, right? So by changing the delay or manipulating the delay value, we only impact EIGRP. It doesn't impact quality of service. It doesn't impact Ospf. And so that's what we want to do. So let's get into, and let me double check this real quick. What interface did it think? For the 4 is going to be to router 3. So it's selected gig 01. So let me go on to gig 01 here. And let's get into global config and interface gigabit Ethernet 01. And I'm going to say delay. And if I do, and actually, let's see what the delay is. It should be 10. Do show IP interface, or I'm sorry, do show interface gig 01. And the delay value should be 10. And it is. You can see right there. Oops, sorry, as it keeps moving in front of me. So the delay is 10 microseconds. So if I was to say delay 1, if I say delay 1, remember, the value I'm entering in here is tens of microseconds. So by saying delay 1, when I say show interface, it's actually going to show me, and let's run that command again, do show int gig 01, what we should see for the delay value is 10 microseconds, right? Because remember, whatever, and this is the confusing thing about EIGRP with the delay value, is when you go to change it, the number that you put in is just add a 0 to the end of whatever it is that you put in, right? So if I put 1, it's going to be 10 when I run that command. So let's do this. Let's change it to 2, meaning the delay would be 20. And let's see what happens. Now, maybe EIGRP is going to choose a different route here, but we'll find out in just a second when I say do show IP route, and we look for the loopback address on router 4, or the loopback for router 4, and let's see what direction it likes. We'll take a look at that. So you'll notice that the values change there. So now it has 2 equal cost paths. So I'm going to up the ante a little bit here, hoping that it doesn't force it into active. I'm going to change the delay, to 30 microseconds. And then let's run that do show IP EIGRP or do show IP route command. And let's see if the values have changed. And we should be down to a single route that's been selected. And take a look. You can see that now, because I'm increasing the delay on this interface to router 3, EIGRP says, well, the better way for me to go is out gig 00 over to router 1. And you see here, it's 131.328. So I'm going to do this. We're going to change the delay here on gig 01. I'm going to change it to 40. Oh, actually, we just leave it at 30, right? So I'll leave it at 30. Let's go into interface gigabit Ethernet 00, and I'm going to change the delay to 20. So let's go ahead and say delay 2, and 20 microseconds. So I'll say delay 2. We'll say show IP route, and let's see. And where did my show IP route command go? There we go. And let's see if the value has changed. And it should change, right? Because the cumulative delay has increased. And actually, you know what? I've already got those values set. So let me do this. I'll set the delay here to 40. And then we're going to go back into interface gigabit Ethernet 01, and we're going to set the delay to, or I'm sorry, set it to 40. I actually just set it to 400. So we'll set the delay, we'll set it to 10 or 100 microseconds here. And so let's go ahead and say do show IP route. And again, what I'm trying to show you is that I can change the value. The feasible distance will stay the same, but the computed distance will change. And so here's the 4444. So you can see right now, the computed distance is 133376. So let me go ahead and say, do show IP EIGRP Topo. And let's check out the 4444, and let's see, it should show me and there it is. All right, so you can see we have a successor and we have a feasible successor. And this is kind of where we're going to, come on, stop. All right, we need that back. There it is, right here at the top. All right. And the screen moved on me there just a little bit. Let's try to bring that back. Okay, so it moved. There it is. All right, so here is that 4444 network. And what you can see here is the computed distance. And you'll notice, take a look, and actually we were able to do that. So this actually did exactly what I was anticipating it would do. So let's take a look here. So here is the feasible distance. But is that the same? No. What about this? No. And that's what I'm trying to prove, is that these two values here, while initially, when the route is first learned and goes from active to passive, these values, or for the successor, the best route, the feasible distance is the same as this value here in the parentheses, the first value. And that's why people often mistakenly say that's the feasible distance, but it's not. That's the computed distance, because the computed distance value can change, right? And you see right there it did, because the delay, the serialization delay changed, making the routes increase in cost because we increased the delay. But there's our original feasible distance for the 444 network, right? So that worked out well. So, and this is a great time to talk about, so we've talked about reported distance, right? So when router 5 gives the route for the 9999 to router 4, it says, hey, I'm reporting to you my cost, my distance to get to the loop back of router 9. That's reported distance. We've talked about feasible distance. Feasible distance is a point-in-time snapshot of the cost when the route first goes from active to passive. And you want it to be in passive. That's what that P stands for on the left-hand column there. Passive means everything is kosher. Everything is cool. We're good. When it goes active, that means the diffusing update algorithm is trying to calculate and find the shortest path. You don't want that because that could interrupt the flow of traffic, right? So we've talked about the computed distance, which is this value here, which is the same value you see when you say show IP route, right? Because that value can change. It's the computed distance, not the feasible distance. So it's the feasible distance and the feasibility condition that ensure loop freedom in EIGRP at all times. And here's what I mean. So we look at these values. Let me clear the screen here. So we look at these values for that 444 network, right? And you can see it clearly states one successor. The successor is always listed first. So the best route is this route right here, the top one, to go through 10.3.13.3. And we know it's the best because the delay on the outgoing interface here to router 1 is 400 microseconds, right? Going this way, it's only 100, because I think those were the values we used. So anyway, lower to go on the southbound route. Now, the feasibility condition states that in order to be a feasible successor, and a feasible successor is not the successor. It can be, but in this case, it's not, because the costs aren't the same here, right? The computed distance values aren't the same. So those are not both successors. And again, it says one successor, and the successor is always listed first. So EIGRP has this really cool thing it does by default, which is it evaluates all the paths that it can take. And if it can determine that there's a backup path that guarantees loop freedom, and the way that it determines that is, does the route meet the feasibility condition? Okay, so in order to be a feasible successor, in other words, in order to be a backup router, right? And in this case, router 1 would be our feasible successor. Router 3 is the current successor, because the current, he's basically thinking like, I succeed, I'm the winner, right? So router 3 wins the lowest cost path. And that's what you see right here. The outgoing interface, gig 01 over to the 10.3.13.3. That is the successor. He wins, right? Because he's got lower delay for 13 to get over to 3. Now, EIGRP says, okay, I've got my best route. Now I've got this other one over here, but is it loop free? So in other words, can I keep it as a backup so that if this link goes down for whatever reason, or maybe something happens on this interface here, is that still going to be, is that a good backup? Can I guarantee that it's loop free? And here's the feasibility condition. This is what the feasibility condition states, and this is where it gets a little bit crazy. So the feasibility condition states that if the reported distance, or I'm sorry, if the feasible distance or the computed distance of the current successor, and I think I'm saying that backwards. Let me check myself here. I'm sorry. Yeah. So if the reported distance, I can never get this right. Hold on, give me 1 second here. I'm actually going to have to check this. Yeah. Yes, the reported distance received for that route must be less than the feasible distance calculated locally. And that guarantees loop freedom. So what we're saying here is, for a route to be considered a backup, the reported distance that's received, right? So router 13 is receiving the reported distance of 131.072 from router 1. So router 1 says, hey, I want to be the backup, and I'm reporting to you that my cost, my distance that I'm reporting to you, the reported distance to get to that loopback address on router 9 is 131,072. So if the reported distance is strictly less than the feasible distance of the current successor, and here it's the computed distance really. If it's lower than that computed distance, it meets the feasibility condition. So in other words, router 13 says, yeah, my best path is to go this way to router 3. That's the lowest cost. But hey, I've got this other path over here, and router 1 is telling me that to get there, the cost for router 1 is 131,072. So router 13 is going to look at that reported distance value and compare it to the feasible distance, or, we manipulated a bunch of things here, the computed distance or the feasible distance of the current successor. And if this is strictly less than, and I'm stressing strictly less than because it cannot be equal to. If it's equal to, you can't guarantee loop freedom going this direction. And so then the diffusing update algorithm is going to have to recalculate, right, to ensure loop freedom. And that's the feasibility condition. Now, if it's a feasible successor, when you say show IP EIGRP topology, it will be listed under the current successor, right? Because it is your feasible successor. It's like a hot standby route, waiting, right, for this link right here between router 13 and 3 to explode or to go down. Or if router 3 goes down, right, router 13 will in milliseconds roll traffic over to router 1. And this is something EIGRP does by default. Now, let's talk about what happens if this is not a feasible, if router 1 is not a feasible successor and router 1 does not meet the feasibility condition. It won't show up here in the show IP EIGRP topology command. So let's come on to router 13, and I'm going to do something else here. And I'm doing this for demonstrative purposes on 13. I'm going to change the bandwidth on that interface, and I'm going to lower it. And I'm going to lower it substantially. So gigabit Ethernet 00. And to do that, I just simply say bandwidth. And you put the value in kilobits per second. So right now, it's 1,000,000 kilobits a second. Well, I'm going to change it to 512 kilobits a second. And let's see if I lowered it enough so that that path to router 1 is not going to meet the feasibility condition. And then router 1 would not be a feasible successor. And we can see this by saying, do show IP EIGRP topology. And there it is. And let's go back and find, and we should see this for basically all the routes that are going to be over here on this side of the topology. But let's double check here. And it looks like it might not have succeeded. Like, I don't think I lowered it. Yeah, because you can see I didn't lower it. Whoops, and it's still going here. All right. So if we were to look at the route over here to router 5, I mean, you can see that 5 is reporting. You know what I did? I'm sorry. So let me do this. It's going to be on router 1 where I want to do this because I want to tweak the reported distance for router 1. So sorry about that. I was thinking 13, but I wanted 1, and we want the interface that goes to router 2. And so let's go ahead and say show IP interface brief. And the link over to router 2 is gig01. So into global config, interface gigabit Ethernet 01. And let's go ahead and say bandwidth 512. Because now router 1 is going to be reporting a distance to get to all of the routing information over here, which is going to be, it should be much higher. In fact, it should be high enough to where here we see that router 1 is no longer a feasible successor. And you know what? I think I might have to tweak the link over to router 3 as well. And let's see what happens here. And no, we don't. Okay, good. So take a look at what happened here. So remember, when we had, come on, stop scrolling, stop scrolling. There's just this terrible delay here between when I hit enter and when it scrolls it all out. So here it is. So take a look now. So now when I say show IP EIGRP topology, router 13 only sees the successor. There is no feasible successor anymore, meaning the reported distance from router 1 to get to the 444 network, that reported distance is strictly greater than or equal to, I should say, it's greater than or equal to the feasible distance of the current successor. And we could say the computed distance as well, right? That value right there. So how do we see that though, right? How do I see what other other candidates for feasible to meet the feasibility condition didn't meet it? And the trick to that is to say show IP EIGRP topology all links. And all links is going to show me the paths that qualified as the successor, any of those that are the feasible successors, but it's also going to show me all of those candidates that didn't meet the feasibility condition. And we're looking for and there it is right there. And this is a fantastic example of what we're talking about, right? So remember, to be considered a feasible successor, to show up when you say show IP EIGRP topology, to show up under the successor, that's our successor right there, to show up under the successor and meet the feasibility condition and to show up in that show IP EIGRP topology command, your reported distance has to be strictly less than the current computed distance of the current successor. And when you look at those values right there, it is obvious that this value here that router 1 is reporting is greater than the current computed distance, right? It doesn't meet the feasibility condition. So we don't see it as a feasible successor. It's not sitting there as a hot standby route. And if this link goes down, EIGRP is going to have to reconverge and Dual is going to have to then calculate and check to see, okay, is that path going to be loop free? Because right now, I can't guarantee that. And so that's the feasibility condition. That's the condition that has to be met to be a feasible successor. And think of feasible successor as nothing more than just, you know, a hot standby path, right? That hey, I'm here. And if the primary path, if the successor goes away, I'm a feasible successor. So you can then use me immediately because I've already guaranteed loop freedom. All right. So now what we're going to do is we're going to take a look at the final thing we're going to talk about tonight. Again, we're going to get into more EIGRP and we're going to come back to this topology next week. But what I want to show you now is how do you convert a classic mode configuration to the named mode configuration. And so to do that, we say router EIGRP1, and we come in here and we say EIGRP Upgrade Cli, and then I've got to give it a name. That's why they call it named mode. So we're going to name ours CCIE, and I'm going to hit enter, and it's going to ask me, hey, are you sure you want to do this? Remember, this is hitless. You can do this in production environments. It's going to convert the config, and everything is going to work fantastic. And I say yes, right? So now, when I say do show run section router EIGRP, and you can see it gives you a message telling you the conversion is complete. and I hit enter, it's going to look a little bit different because now we're dealing with address family configuration. And you can see, right, we're in the address family for IPv4. Now, this is a resync, but that is not a tearing down. It's a graceful resync. We're not tearing the neighbor adjacency down. So again, this is something you can do on the fly. And so take a look at what we've got here, right? You've got your router EIGRP in your name, the address family for IPv4 unicast autonomous system number 1. These are EIGRP interfaces, like this refers to all interfaces, and we did that passive interface on all the interfaces. And so here's what that configuration stanza looks like. Now, something else that's going to change are the metrics, right? So if I was to do the same thing over here on router 1, and let's say router EIGRP1, and then let's say EIGRP Upgrade Cli, and we'll call it CCIE, and then we'll say yes. And if I come over here back to router 13, and let's go ahead and say show IP route. And so let's take a look at some of those metric numbers now. And as you can see, these numbers are like crazy big in some cases. And that's the extra granularity that is introduced when we're using named mode or 64-bit mode that gives us that additional granularity, right? And so the metric values are going to get larger. So what I'm going to do, not here in this video, but we've gone for 90 minutes. So this is going to be a good place to go ahead and break for the night. And let me make sure that there are, yep, and you are very welcome. And so there were no questions. And so what I'm going to do now is I'm going to go ahead and cut the recording off here. When we pick up next Sunday evening, or this coming Sunday evening, we're going to jump right back in here with named mode. And then we're going to go in and start talking about the different ways to configure things with name mode. We're going to talk about summarization. I'm going to introduce some IPv6 so that we can see the multiple address families and what that would look like. All right, guys. Well, thanks so much for attending. And let me know if you have any questions throughout the week. Have a great night and have a great rest of your week.